Welcome to an exciting educational content video brought to you by Chrysolite Tutors. Today, we'll be looking at this course, Math 106, and it is meant for Management Sciences second semester for students in the National Open University of Nigeria. Today, in this unit 1, we'll be looking at sets and subsets. And the theory of sets lies in the foundation of mathematics. So it is a concept that rears its head in most fields of mathematics, pure and applied. So at the end of this course or this video, we'll be able to identify some sets from given statement, rewrite sets in different set notation, identify the different kinds of sets with examples. So stay tuned to the end of this video to get all the concepts about sets. Sets is a set. A set is any well-defined list, collection, or class of objects. Examples of sets include number 1, example. I can say the numbers 0, 2, 4, 6, blah blah blah. So this is a set. We said a set is a collection of similar items. Now if you check, this one has to do with numbers increasing by 2. So another set, example 2, is the solution of the equation. The solution of the equation. So I can have a quadratic equation like this: x squared plus 2x plus 1 is equal to 0. Note that for this kind of set, there are 2 elements inside of it, 2 solutions. Okay, so another example, number 3, is the vowel sounds. The vowel sounds. So this is another collection of similar items, the vowel sounds. Now the vowel sounds are only 5. We all know that. The vowel sounds is A, E, I, O, and U. Okay, so this is another set. And we have the people living on Earth is a set. The people living on Earth. The people living on Earth is a set. Okay, there are many examples, but we can just stop here. Okay, I can say a set of students named Tom, Dick, and Harry. So these are 3 elements inside the set. So countries like England, France, and Denmark is another example. Countries like England, France, and Denmark. Note that these countries are in Europe. So you see that there's something similar to this collection of items. Something similar. You just see it. Another one is the number 1, 3, the set of number 1, 3, 7, and 10. Okay, what is similar here? The numbers are increasing by 2, starting from 1, increasing by 2. Okay, well, I think it's just a set of numbers 1, 3, 7, and 10, just finite. Okay, number 8 here, I would say rivers in Nigeria. So it's another form of set. So, like I said initially, set is the collection of similar items. So note that some of these sets, there are sets of odd numbers in the mentioned example that is presented as for this one now. Odd numbers, you understand? These are sets of odd numbers, okay, except for this one. Okay, so we'll go on to notation. When we say notation, what do we mean? So notations are usually how a set is described. So sets will usually be denoted by capital letters: A, B, C, D, and so on. Understand? So lower cases are used to represent elements in our set. So elements are inside the set. So we can use lower cases to represent elements inside the set. So big cases are used for the uh, set itself, and the lower cases are used for the elements of the set. Elements of the set. Okay, so for example, if we define a particular set by actually listing the members, let's say for instance set A, see big A now. So this is set A. So we'll now come here like this and list the members 1, 3, 7, and 10. We close the bracket. This curly bracket is how we use to denote set. So this is the element. The elements are separated by commas. Understand? And these elements are enclosed in a curly bracket. We call this the tabular form of sets. So another way we can denote sets, for instance, we can say state in words and then write in tabular form. Okay, so I'll say state in words, like an exercise, state in words and write in tabular form. So this is tabular form. So if I come here and say number 1, A is equals to elements such that, A contains X such that X square is equals to 4 square. Then I close the curly bracket. Or I can say B is a set such that the element X is X minus 2 is equals to 5. So how can I represent this? How can I write this in a tabular form? Okay, so but I will just quickly say that A reads, A is the set X of X such that, this line here means such that X square is equals to 4 square. The only numbers which can be written, or which can give is, okay, this is not the square. Okay, so the only number this can give is where X is equals to plus or minus 2. Or I will come here and say A is equals to 2 and minus 2. Close the bracket. That's what this thing can give. This is this in tabular form. So this is reading X, A element of X such that X squared is equals to 4. So these are the elements inside in the tabular form. Then for this one, it says B reads X such that X minus 2. This line here is such that X minus 2 is equals to 5. The only solution for this one is when minus 2 goes over to the other side, it becomes, I'm solving this equation. When minus 2 goes over to the other side, it becomes 7. That is plus 2. So plus 2 plus 5 is 7. So X is equals to 7. So there's only one term or element inside this set, which is 7. So these are known as finite sets. We'll talk about it later, but just want us to know the notations of sets. Okay, so I'm going to give some exercises quickly. We should write this set in the set builder form. Let me put it on the board first to attempt it. Even as I'm doing that, I want us to be actively putting it in the comment section. Okay, so write this set in the set builder form. Write it. Write these sets in a set builder form. Sometimes your TMA, this is how the questions will come out. Set builder form. Okay, so number 1, let A consist of the letters A, B, C, D, and E. Okay, then number 2. So I have on the board that we should write these sets in set builder form. Okay, so I'm going to be doing a solution here. I'll just do one solution clean, do one solution clean. There are 5 questions that we have here. So for that number 1, he says let A consist of letters A, B, C, D, and E. So the set beta form representation of this is A is equals to X such that X appears before F in the alphabet. Before F in the alphabet. This one is simple enough. It's simple enough. You know why? Because all these letters A, B, C, D actually appears before F. So this is the set beta form for that question. So number 2 question, set beta form for number 2, it said let B be 2, 4, 6, 8, blah, blah, blah. So I can come here generally and say B is equals to a set of element X such that X is what? Is even and positive. You see these words I'm using now is describing everything here, because this is infinite. It's infinite. After 2, 4, 6, 8, then blah, 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 blah. You continue. That's what this one means. You continue. So this in set beta form actually define what this thing is. B is equals to element of the of element named X such that X, which is the element, is even and positive number. X can represent anything here. Okay, so number 3 in set beta form. Number 3 in set beta form is also very easy. So it said let C be the country, consists of countries in the United Nations. So I'll come and say C is a set such that it contains element X, or C contains element X such that X is a country in the United Nations. So that X is a country in the United Nations. Very easy. Very easy. Very easy. And number 4. Number 4 says let D is equals to 3. Let D is equals to 3. So we can play around with this. Anything can go. Can write an equation for this type in set beta form. I can come here and say in set beta form D is equals to element X such that I can write an equation X minus 2 is equals to 1, for instance. I can close it. This one is correct. You understand? I can also say such that I can say D is equals to element X again such that 2x is equals to 6. You can play with this. Anything that the solution will give you 3 is correct. Okay, so that's the set beta form. Okay, this is just to help us to build our understanding of sets. It's not the main thing. This is just to help us build understanding of sets. Number 5, it says let E be the heads of state. Obasanjo, Yaradua, and Jonathan. We all know that these 3 gentlemen were presidents of Nigeria. So in set beta form, I can say E contains element X such that X is what? The head of state after Abacha. X was the head of state after Abacha. Note that there's an order in sets. So we know that after Abacha, okay, we now had Abdusalami Abubakar. Okay, so I can even put Abdusalami Abubakar. Okay, here. So I'll just put Abdusalam here. Abdul Salam. Anyone can go. Abubakar is correct and Salaka is correct. All right. So these are writing sets in set builder form. So the next we go to finite and infinite sets. So we have on the board finite and infinite sets. What are finite sets? So sets can be finite or infinite indefinitely. A set is finite if it consists of a specific number of elements. That means if I come here and say A is equals to the element 1, 2, 3, and 4, I close it, I stop here, I don't continue, I don't put dots like this. So these are elements, there are 4 elements in this set. This set is a finite set. Okay, now another way, another kind of set can be infinite. Let n be, let me call this one finite set so you know, finite sets, all right? So if I have this n, set n, contains 0, 2, 4, 6, 8. Then I put continuous dot like this, showing that it never ends. So this is an infinite set. So these two kinds of names I have here denote the kinds of sets this one represents on the board. So if I come and say let P be equals to element X, okay, such that X is a river on Earth. What do you think this kind of set is? Is it finite or infinite? Can you quickly put it in the comment section? Okay, so but although it may be difficult for us to start naming all the rivers in the world, but P is still an infinite set because we cannot have more rivers that actually is on Earth. So that is it. So we move on to the next one. Equality of sets. Equality of sets. Okay, so I have on the board equality of sets. So a set A is said to be equal to set B if both have the same element. So we'll write it like this: set A is equal to B if they have the same number of elements. For instance, let set A be 1, 2, 3, and 4, and B is equals to 3, 1, 4, and 2. See? So A is equals to B. Why? Because the number of elements or the elements are the same. So I have 1 here, I have 1 here. I have 2 here, I have 2 here. I have 3 here, I have 3 here. And I have 4 here, I have 4 here. So irrespective of how it's arranged, in the array, in the set, if they are the same element, then they are equal. Okay, so set A and set B are equal. Why? Because they both have the same members. They both have the same members. That is, every element which belongs to A also belongs to B. Okay, so let's see. Okay, like I said, it does not matter how the sets are arranged. Okay, now a null set is another kind of set. I'll just put it under here, null set. Null set. A null set is a set that is empty. It's an empty set, nothing inside. So we say that such a set is void or empty. We denote it by this symbol. So if you see this symbol anywhere, you see that it's a null set. For example of a null set. Okay, let's set A be set of people in the world older than 200 years. Do we have people like that in the world? 200 years old? I don't know, no statistics like that. So this set is a null set. It's a null set. According to statistics, we don't have anyone, even in Guinness Book of Records, who is alive up to 200 years. So we just looked at null sets and equality of sets. Okay, so we have subsets. So if every element of set A is also a member of set B, so it is known as a subset of a subset. Okay. Okay, so more specifically, A is a subset of B if X belongs to B. So um, A is a subset of B if A is a subset of B, okay, if X is a member of A. So I said A is a subset of B if X belongs to A and X also belongs to B. This symbol is belongs to. Understand? So we denote this relationship by writing, simply writing A belongs to, sorry, is a subset of B uh, or contain. Understand? This is read. This is read. A is contained in B. This is how this is read. Understand? So this is a subset. So A is contained in B. So I will just quickly share some examples. So for instance, if I have set C, and these are the elements in set C. Okay. So if this is element in set C, is this one is a subset of this element of this set. Let me see. Is equals to D is equals to 5, 4, 3, 2, 1. You understand? So this is a subset of this. Why? Because every element here is also present inside this bigger one. You understand? Okay, so since number 1 belongs to, this is 1 here, belongs to C and belongs to D. Number 3 belongs to C and belongs to D. And number 5 belongs to C and belongs to D. Therefore, C is a subset of D. C is a subset of D. I'll quickly give another example. Okay. If I have set E, and set E has this element, it has 2, 4, 6. Understand? And F has this element 6, 2, 4. This is very interesting. So since number 2 is contained or is belonging to E, also belongs to F. See number 2 here. Then 4, you understand, belongs to E and belongs to F as well. 6 belongs to E and belongs to F. Then E and F are actually equal in a similar manner, but it can be shown that it's also a subset. You understand? So this one has dual functionality or dual naturality. It behaves in two ways. It behaves as E is equals to F. Why? Because everything here exactly is the same thing as everything here. But it can also be that E also belongs to F. So this is the dual nature of this particular set of example that we have here. So two sets A and B are equal if A is equals to B. If and only if A is a source of B and B is a source of A, then we can claim that B is also a member of A. Now I'm going to write this statement on the board so that we can understand what I'm trying to say. So if for instance, two sets A and B are equal. How do you write equality of set? A is equals to B, right? Okay. Now, if and only if A is a subset of B, and B is a subset of A. See, they are you see how it is, like that case I gave where they are equal and at the same time subset. So these are the two things. So if A is a subset of B, then we can also write that B contains A. So this is a subset of B, but B contains A, which is read as so this one is read as what? B is a superset of A. So if the curve is going this way, such that this one now is carrying the open end of the curve, so that is a superset. Superset means that you might have more elements than what you have here. You understand? Now, like the situation where you have A is equals to 1, 2, 3, 4, and 5. Then B is equals to 2, 3, and 4. You know that A is a superset of B. Why? Because it's actually bigger than B. Yes, and bigger than B. But B is a subset of A. Why? Because this one can contain here. But we're looking at a situation where you have equality at the same time. It can also be described as a subset or superset, as the case may be. Okay. So conclusively, you can state that the null set, we're trying to conclude, the null set is considered to be the subset of every set. Yes. Yes, this is very, very important. The null set is of every, so you can see this in your TMA, your tutor mark assignment. You can see this in your TMA, say, or in your exam proper. So note the following. Note number 1, the null set is considered to be the subset of every set. To be the subset of every set. Is the null set does not have any effects. It's empty. So it can be in every set. And if A is not a subset of B, so number 2 point to note, if A is not a subset of B, that is, if A does not, so you see, does not belong to B, or a subset of B, then there is at least one element in A that is not a member of B. So if A is not a subset of B, that is A does not is not a subset of B, that's how it's written. Then there is at least one element in A that is not a member of B. Okay, so note these 2 points. So we'll go to the next one, proper sets. So we'll look at the concept of proper subsets. So since every set A is a subset of itself, so every set is a subset of itself. Okay, so we can call B a proper set of A if first is a subset of A and secondly it's not equal to A. So this is the concept of the one I said that okay, some the set is bigger than the other set. For instance, now B is given us the following 1, 2, 3, and A is given as 1, 2, 3, 4, 5. So you see this now. A B is a subset of A. Why? Because every element in B is in A. But now this kind of subset is called a proper subset because B and A are not equal. A is bigger than B because we have extra elements in A. But at least everything in B is inside A, but they are extra. So these and these are not equal. If they are equal, this is not a proper subset if they are equal. But if they are not equal, then this is a proper subset in such that everything here is here. So this is how it is written. Yes, and this is how it is written. Some textbook will write it like this. You understand? Uh, sorry, this is the proper subset. You understand? So, but the one that is equal and equal and subsets like this, they put the equality sign there and they put the proper, the subset sign there. Okay, so we'll go to the next one, comparability. Okay, so two sets A and B are said to be comparable if A is a subset of B or B is a subset of A. Understand? So if A is a subset of B or B is a subset of A, they are known to be comparable. But if they are not subsets, if A is not a subset of B or B is not a subset of A, then they are not comparable. So let's, for example, now let A is equals to small letter A and big letter small letter B. Okay, that's lowercase a and lowercase b, and then B is equals to A, B, and C. Okay, so A is comparable to B since A is a result of B. See, the elements in A are inside elements in B as well. So that is a comparability. They are comparable. Okay, so let's go on to the next one, sets of sets. Sometimes it happens where we say that the objects of a set are sets themselves. For example, the set of all subsets of A. So in order to avoid to say a set of sets, so it's a common practice to say family of sets or class of sets. So under the circumstances and in order to avoid confusion, we sometimes will let script letters A, B, C, for instance. So for if we come here and say uh, uh, the set like this, and we now put a big set like this, big curly uh, bracket, and have some smaller curly bracket inside. So I have this like this, then I put a comma here. I have another. You get the point. So this is 5 and 6, for instance. Another curly point like this. Okay, so we have something like this. So this is sets inside a bigger set. So the element of this set is sets themselves. That's why we call it sets of sets. Understand? So we see this in geometry. We can always say family of lines or family of curves, since lines and curves are themselves a set of points. So theoretically, it is possible that a set has some members which are sets themselves. So and some members are not just sets, which are not just sets. Although in any application of theory of set, these cases arise infrequently. So it's not a very common scenario. So we move on to universal set. Universal set is just the mother of all the sets, universal sets. So it's just like the umbrella sets. Understand? So in any application of the set theory, all the sets under investigation will likely be subset to a fixed set. We denote that one by U. By U. So we'll be seeing that very soon. So power set. Power set is just a family of all the sets of any set S. You understand? Is raised to the power of S. So if I have power, this is power set. Power set. So if uh, we have uh, M, for instance, M is a set of this number of this element A and B. Okay, so therefore 2 raised to the power M like this is the same thing as saying I will now list all these sets. You understand? List all these sets like this. I will list there's a small set inside that contains A and B like this. Then I'll put the set of only A. I'll put the set of only B, and I will put the empty set, the null sets, the null sets. So this is power sets. Power sets is just like the uh, uh, the power, 2 raised to the power of the set itself. So you have this set here, that's the set itself as a subset. Then you have one element of the set as second sub element. Then you have the second element of the set, and you then have the empty set. So this is the power set. So it's a set S is finite, uh, and if it has n elements, then the power set can be shown to have 2 raised to the power n elements. So for this situation now where the elements are 2, the power set should be 4 elements. It should be 4 elements. If the number of elements here are 3, let's say for instance I come here, let me just put it here. I have n here is equals to A, B, and C. So the power set is 2 raised to the power n. That is the number of elements inside here. Understand? What is the number of elements inside here? N is 3, 1, 2, 3. So 2 raised to the power 3 is equal to 8. So I should have 8 elements in the power set. How can I have the power set? 2 raised to the power n is equal to the first element in this set is all the set first. That's everything first. Number 1. Number 2 is A, B, C. That's 1, 2, 3, 4. Then 5 is A and B, or B and C. 6, 7, you understand? So 1, 2, 3, 4, 5, 6. So it remains 2. I've not put A and C. And the final one is the empty set. Hope you get the point. Get the point. I don't want to go further than this. Just know that power set is the set. You take 2 to the power of the element of that set. So the result of what you get by raising 2 to the power of the element of that set is the number of elements in a new power set. So the first thing you do is that for power set, you want to list them. All the elements in that mother set will be the first element of the power set. Then you can list the individual elements first, then you do a combination, and so on and so forth until you get to the empty set. So you have disjointed set. A disjointed set is a set that no elements are in common. No elements. Okay, let me give you an example. Sorry. Disjointed sets quickly. Okay, so if set A disjoint sets. Okay, So if set A and B have no elements in common, as in nothing, no intersection. So if no element of A, another way to put it, A is in B and no element of B is in A, then we say that they are disjointed sets, or disjoint, this A and B are disjoint. Okay, so the example they gave in your material, they say A is equals to 1, 3, 7, 8, and B is equals to 2, 4, 7, 9. This is not an example of disjoint set. Why? Because I have a common point here. These are the common points. If this one does not exist, for instance, then I would say they are disjoint sets. You understand? They are disjoint sets. So this is not a case for disjoint sets. Okay. So finally, okay. So a simple and instructive way of illustrating relationship between sets and the elements inside the sets is the use of the so-called Venn-Hillier diagram, or you can just simply call it Venn diagram. So Venn diagram is just a way of representing sets. Most of the time we use circle to represent a set. So if this is a set and inside there are elements, so I'm putting the element like this. I told you that the big capital letters are used for sets and little letters, the lowercase, are used for the elements. So these are elements inside this set. So this is a Venn diagram. This is a diagram representation of the set. So sometimes you might have the universal set. I talked about the universal set, that is U, for instance. Then you can have different sets instead of U. Universal set, you have A, B, and C, for instance. And in this particular case, they are all meeting at a point. Set A and set B and set C are meeting at a point. You understand? So I can have 1, 2 inside, I have 3, I have 4 here, I have 5, I have 7, I have 6, I have 8 and 9. Now, the way this thing is now, you can see that in set A, this is set A. Set A is bounded by this circle like this. So everything inside this circle is set A. If I want to give label set A, I will just say the elements in set A is 1, 2, 3, 4, 5. See, 1, 2, 3, 4, 5. The key word is that it is bounded by everything inside the circle. So for set B, this set B, I want to label the element. I say 3, 4. See where the marker is going. This is every number, every element that falls in between this circle is the element of B. So it's 3, 4, 7, 8, and 9. And then for C, look at my marker again. It's going around like this and comes like this. So the element of C is 4, 5, 6, and 7. Now, you know that there is an intersection of everything. This 4 is present in A, B, and C at the same time. Look at it, 4, 4, 4. This is the intersection of all the elements, all the sets. We will talk about set operations later, when you see the union and intersection, this intersection and this union. So we'll see that later in this course. So we have been able to talk about sets in a way that you can understand. Introduction. We look at the sets is any well-defined list or collection of or class of objects given a set A with elements 1, 2, 3, 4, 5, 7. We saw it. There's a tabular form to represent it. There's a set builder form to represent it. Please take note of these forms. Then we talked about equality of sets. We talked about null set. We talked about subset, proper set, power set. And then finally, we looked at the Venn diagram. So I hope this video has been informative for you. Please like, share, and subscribe to our channel to get more content of our videos. Thank you for viewing.